Hello everyone, welcome to my talk. I am Shashank Prasanna at AWS, and today I'd like to share some best practices for how to choose the right EC2 instance for your machine learning inference workloads so that you can improve performance, productivity, and save on costs. So here's the agenda for the rest of our talk. I'll start off with some of the challenges with machine learning inference, and as you know, challenges with training can be very different from challenges you face when doing machine learning inference. We'll then take a look at some key considerations such as throughput, latency, cost, what kind of models you're deploying, and also how easy it is to go from a model to production deployment. You want to take a look at all these different considerations as you make your choice. And then we'll take a look at the different instance types available to you. These include CPU instance types, GPUs, Amazon Elastic Inference, AWS Inferentia. If you don't know what these are, then we'll go through what these are and give you some steps on how to choose the right option. We'll take a look at plenty of examples, which each of these options will wrap everything up with summary and Q&A. So with that, let's get started. Let's say you have an application that you're hosting in the cloud, and this application has a machine learning model as a core part of your application. And in many cases, the model inference tends to be a bottleneck in your entire application and affects customer experience. Your customers may be accessing your application via mobile phones, web apps, or other microservices, and there are a few considerations that affect customer experience. One is, what is your round trip latency? If you have a conversational assistant, then if it takes several seconds to respond, then that's just not good customer experience. And if you're not able to scale to large number of customers or millions of customers, again, that may not be good customer experience. Even if you're able to hit on your target latency and your target throughput, but if you can't do it under your budget, then the option may not be viable to you. In fact, you can actually make sure that you reach these goals by using an AI accelerator. Traditionally, an application that looks like this may have some application logic, some pre-processing steps, your machine learning inference, and then post-processing and application logic. Traditionally, the entire stack runs on a CPU. In order to speed up this application, you can still continue to run your traditional application logic and pre-processing, post-processing steps on a CPU, which is really good for high-performance serial tasks such as these, and offload the machine learning inference to an accelerator such as a GPU, AWS Inferentia, which is a custom machine learning chip, and Amazon Elastic Inference, which gives you variable size GPU acceleration. By offloading, you can dramatically speed up the performance of your application and reach your target latency throughput goals by staying within your cost budget. Now, of course, there are many options, and where do you start? What do you choose first, and how do you go about choosing the right option for your workload? You may often ask yourself questions about, is a GPU always better than a CPU? Is AWS Inferentia always more performant than a GPU? Is Elastic Inference always cheaper than a GPU or a CPU? The general answer is it's completely dependent on your workload. So what's really important is for you to take a look at some key considerations for your workload, and then decide which option is right for you. So I'll share with you 4 key considerations. The first key consideration is, what is your target performance? And this includes both the throughput, that is how much inference requests you're able to serve per second, and also the round trip latency, how quickly you're able to deliver these results. So having a budget ahead of time will help you make this decision. The second is, of course, cost efficiency. Are you able to keep your instance fully utilized so that you can deliver the right performance under your target budget, cost budget? And the third consideration is, what kind of models are you deploying? Are you deploying off-the-shelf models, or do you have custom models or custom layers that you've written? And this choice is also will also play a role in choosing the right instance type. And finally, how easy is it to go from a trained model to a production deployment hosted endpoint that's secure and highly scalable? And what kind of frameworks you're working with? With these key considerations in mind, we have few different options here that you can choose from. CPUs, you are already familiar with. There's also GPUs and Elastic Inference and AWS Inferentia. Let's start with GPUs, and we'll take a look at each of these options, starting with GPUs by looking at these 4 key considerations. On AWS, if you're doing a training, you already know there are many different instance types, instance family and instance types, and also different instance sizes. And you're probably using NVIDIA V100 with a P3 instance for training already. When it comes to inference deployment, the best instance on the cloud in terms of performance and cost efficiency tends to be the NVIDIA T4 GPU, which is part of the G4 instance type. If you want a summary of all the different instance types on AWS, I've linked a blog post below. Feel free to check that out. Now, with that very quick introduction, I'm of the I'm of the camp that believes that you have to show the results first before you dive into the features and benefits. So let's take a look at a quick demo. And in this demo, I'll do an inference benchmarking task using a ResNet 50 model, which is a popular image classification model. And it has I have about 50,000 images, and I have I should be getting about 74.5 accuracy. So for this model, we'll take a look at throughput, latency, and accuracy while running on a GPU. And we'll take a look at 2 different approaches. One is using your native framework, which is maybe a TensorFlow, Keras, or PyTorch. We'll take a look at TensorFlow. And second, we'll do something different. We'll compile the model with NVIDIA's compiler called TensorRT, and then we'll run inference and see if compiling your model versus just using your framework gives you better results. And this will have an implication on throughput and performance and cost. So let's jump into our demo. So all the code that I show here will be made available to you. I'll share a link at the end of this presentation. This particular example was run on an Amazon EC2 G4DNX large instance, which is a single GPU instance. I'm also using the AWS Deep Learning AMI, this particular version, if you want to replicate your results. And I'm also using NVIDIA's container to compile your models. And let's take a look at the final benchmarking results, and then we'll come back and take a look at some of the code steps that you need to do. So you see here there are 4 columns. The first column is running inference on the GPU using your vanilla framework. So I'm just using TensorFlow, I'm loading the model and running inference. You see I get about 115 images per second here as my throughput, and latency is about 70 milliseconds. Good, maybe this works for you. But we're using NVIDIA TensorRT, I can compile the model, which does graph optimizations and layer fusions and few other optimizations, and also can dramatically improve performance by compiling to reduce precision, such as half precision and integer precision. And let's see what happens when you do that. When you do that, you automatically see here that the throughput dramatically jumps from 115 to 1600, and then 17 and 1800 depending on what precision you're deploying with. The lower the precision, the more compute power the GPU has to compute your inference requests. And this also dramatically decreases the latency. You can get up to single-digit latency inference, which may be very important for your video example or speech example where latency is critical. In terms of usage, deploying with GPUs, it's pretty straightforward if you're just using your deep learning framework, because you just load your model, and then once you load your model, you just invoke the model function with your dataset, and you get results. But if you want to compile, there are a few additional steps involved if you use NVIDIA TensorRT to compile. And these steps include specifying what kind of precision you have, and then going through a conversion step. And you call this convert function after going through these few different steps. A few more steps involved, but maybe it's worth for you to go through these steps because of the huge performance benefits you get. You go through this conversion step, specify the inference precision. In this case, I'm sweeping 3 different precisions with single precision, half precision, and integer precision, and the end result is what I showed you. So this is great. This is the end result. So this is great if you want to just run inference on your local EC2 instance. But what if you want to host a model as a scalable endpoint? This is where Amazon SageMaker will help you. And to use SageMaker to host your endpoint, we call it one-click deploy because it is super easy and convenient to do that. All you have to do is load your model, upload it to S3, and once you load your model, there's a function you can easily upload it to S3. And once you upload it to S3, you have to create a TensorFlow model using the SageMaker SDK. And once you create this model, it's really one line function to host a highly secure, scalable, reliable endpoint. And if you want to deploy it to a GPU instance, all you have to do is specify model.deploy and specify the type of instance. Once you do this, a model endpoint is created for you, which you can then use, invoke it to get requests, as I've done here below. I can test the endpoint. In this case, I'm testing this on a GPU instance, and I get my endpoint results. So that was a quick demo of using GPUs, so you get a sense of what key capabilities are supported. Now let's take a look at some of the benefits of using GPU accelerated inference. From a performance standpoint, GPUs are some of the best options out there for latency and throughput. Here are some benchmarks in this link that I've shared that NVIDIA has shown for benchmark performance. From a cost perspective, GPUs can be very cost efficient, but there's a catch. You have to make sure that your GPU utilization is high. If you can't keep your GPU utilization high, then you're leaving performance on the table. If you're only using 50% of your GPU because your model is small, or if you have sporadic inference requests that are not utilizing the GPU, then your cost per inference goes up. So you have to bear in mind that for GPUs to be cost effective, you have to keep it fully utilized. From an ease of use standpoint, GPUs are some of the easiest options to use because all frameworks automatically come supported with GPU support. And by using NVIDIA TensorRT, which takes a little more extra steps, you can you get far better performance. So it's a trade-off you have to make. If you want to spend a little bit of extra effort, you can get much better performance with GPUs. One of the key strengths of GPUs, in my opinion, is the fact that GPUs are programmable, similar to CPUs. Let's say if you're pushing the boundary of deep learning research and you have custom models or custom layers, and GPUs are some of the first of these options to get support for these layers, either in upstream frameworks like TensorFlow, PyTorch, or MXNet. But if you're authoring your own layers, you typically write it in Python, and which means they're not accelerated on your GPU. But using NVIDIA's CUDA, you can write these layers in CUDA programming language so that it's accelerated on GPUs. As I'll show you with some of these other options with Amazon Elastic Inference and AWS Inferentia, programmability is not an option on those instances, and with GPU you can. So you can always be sure that your inference is running at maximum performance. In terms of what options are available to you on AWS, you have NVIDIA T4 GPUs on the G4 instance type. As I mentioned, they come in these different sizes. There are 5 different options for single GPUs, 2 different options for multi GPUs. And in terms of software, the AWS deep learning software, deep learning AMI and deep learning containers offer all the optimized software you need to run inference, including TensorFlow serving and other software that you may need. And a question you may have is, how do I choose the right instance type for my workload? Because there are 5 different options. They all have single GPUs. How do I choose G4DN X large, and when do I choose G4DN 16X large if they all have one GPU? Well, the answer to that question is that do you have a lot of pre-processing steps? Does your application logic require a lot of compute horsepower on the CPU side? If the answer is yes, then you want to get a GPU instance that has a beefier CPU, like the G4DN 16X large. If you have a very lightweight model, and if you don't have a lot of pre-processing, post-processing steps, then you can get a lower powered CPU instance with the same powerful GPU. And there are also multi-GPU instances if you do want to host multiple models on 4 GPUs or 8 GPUs with these two options here. General recommendation is to always start small and then scale up as you feel that you need more compute. So as I mentioned, one of the key challenges with GPUs is that keeping its utilization high can be challenging, especially if you have smaller models. And the graph here shows that for inference requests, real-time inference requests, when you have sporadic requests coming in, which are small batch sizes, your GPU tends to be heavily underutilized, as in contrast to batch processing jobs where you can actually keep the GPU fully utilized. So at one end of the spectrum are CPUs, really cost-effective options for especially for smaller machine learning models or lightweight applications. At the other end of the spectrum is powerful GPUs that can give you low-cost inference as long as you're keeping it fully utilized, so that your cost per inference is low. But turns out that a lot of real-world applications fall in between. What about mid-size models that are too slow on a CPU and a GPU is an overkill, too much performance for the cost, and you need a little bit of GPU acceleration but not a whole lot, and you also have a higher latency budget. Maybe you have a 200 millisecond latency budget for a good customer experience, but your application, your GPU will give you a single digit millisecond latency. And in that case, can you trade off some amount of performance for cost savings, right? So these are all good considerations. And this brings us to our next option, which is Amazon Elastic Inference. And let's take a look at what this is. With Amazon Elastic Inference, you can network attach variable size GPU acceleration. So rather than get a full GPU instance, you can spin up your regular CPU instance and attach variable size GPUs in medium, large, and extra large, and attach it via the network. The benefit here is that you're still working with your CPU instance, and just when you need the acceleration, you can use the accelerator that comes in variable sizes. So depending on your model size, you can choose different options. With this introduction to Elastic Inference, let's take a look at a very quick demo. So I'll jump over to our Elastic Inference demo. Again, the code will be made available to you. I'm running this example on an Amazon EC2 CFI instance using the deep learning AMI, and I'm going to network attach an inference accelerator via the network, and I can query and see that this particular accelerator has been attached to this EC2 instance. Notice the GPU acceleration is not on the CPU instance, it's somewhere else that's attached via the network. So let's take a look at the final results that compares the performance difference between CPU only inference and using Elastic Inference. So what I'm doing is I'm doing a side-by-side comparison of running inference on the native CPU, which is host CPU, which is a CFI instance CPU, and then running inference on this Elastic Inference accelerator. You'll see that just by running on a CPU, my throughput tends to be about 26 images per second. Good, okay. And the latency is pretty high at 300 millisecond. But if you have a 100 millisecond latency budget, and you don't need 5 millisecond latency budget like you get with a GPU, with using Elastic Inference, I can get much better throughput at 160 images per second about, and 50 millisecond latency. So that is a huge benefit at a substantial cost savings compared to using a full GPU instance. In terms of how to use Elastic Inference, the deep learning AMI has Elastic Inference enhanced frameworks that give you access to APIs like these. So rather than load the model into the framework API, you'll use the Elastic Inference for TensorFlow API if you're using TensorFlow to load it. That's the only difference in your code. So when you do that, let me show you what this looks like. When you load the model, you'll use EI predictor to load the model rather than the TensorFlow's load function, and the rest of the code is the same, and you get this performance improvements. So that's using Elastic Inference. Let's take a look at some of the benefits of Elastic Inference. So in terms of performance, Elastic Inference will give you lower performance than a GPU instance, will give you higher performance than a CPU only instance. And it's the ideal option when you want something in between, right? And from a cost savings perspective, elastic inference is one of the best options out there. You can get 75% savings in cost versus a full GPU, as long as the elastic inference accelerator is giving you the throughput and latency budget performance to meet your goals. And in terms of ease of use, it's very easy to use using the elastic inference enabled frameworks. Things just work out of the box for you. And it's also easy to use it with Amazon SageMaker hosting. The same process as I showed you before. One-click deploy, just specify the inference type, and I'll show you very quickly what that looks like using elastic inference endpoint. Elastic inference, you can just introduce it to the model.deploy function by specifying the accelerator type, and the rest of the process is the same. And there are many different options. There are 6 different sizes, as I mentioned, different memory sizes within each of these instance type, and different teraflops. And in terms of how to choose, there are 2 considerations that you need to make. The first consideration is what kind of host CPU do you need. You want to make that decision based on, do you have a lot of pre-processing, post-processing steps? Then you want a beefier host CPU. If you don't, then you can get a lower, lesser powered host CPU. And the second consideration is how to choose the elastic inference accelerator size. And this is completely dependent on how much memory do you need. They come in different sizes, 1 GB to 8 GB. So how much memory do you need in the accelerator for your model, and also how much teraflops you need. That's purely a measure of performance. The general recommendation is to start small and scale up as you need more compute. So we saw GPUs and elastic inference. We also compared it with CPUs. So let's take a look at our final option, which is AWS Inferentia. And AWS Inferentia is a custom machine learning silicon developed by AWS. And this is a high performance silicon purpose built for machine learning inference, and can give you some of the best performance and at a huge cost savings, because it's also one of the lower cost options. And in terms of architecture, there are 4 neuron cores per chip, and this becomes important as you start to decide what kind of instance type you need. You also get different precision supports. It supports reduced precision all the way up to FP16, bfloat 16, and integer 8. Also has very fast chip-to-chip interconnect, and this becomes important when you want to do model parallel. Let's say you want to split your model and host them on different cores, then the fast chip-to-chip interconnect makes sure that you get very low latency performance. So again, following the same format, let's take a look at a demo so it becomes clear how to use AWS Inferentia. We'll try something different here in terms of the approach. Rather than compare and contrast with GPUs or CPUs, I'll show you different ways to optimize inference on AWS Inferentia. We compare 3 different options. We vary the batch size, and also we vary the number of cores you want to run this on. And these are optimizations that you want to consider as you consider your deployment, because one of them may give you better performance than the other. So let's go back to our final demo. I'm running this on Amazon EC2 Inf1X large instance, and again I'm using the deep learning AMI to run this demo. And let's jump back to the end and take a look at the final results. So I'm comparing 3 different things here: batch size 1 compiled for 1 course, batch size 5 compiled for 1 core, and batch size 1 compiled for 4 cores. AWS Inferentia offers a compiler, and you have to decide ahead of time what batch size you want to compile it for, and also how many cores you want it to use. If you want it to use 1 core, you have 4 cores on a chip. So then what you can do is replicate the model on the 4 cores, so that each of them are processing requests in separate threads. Or you could alternatively, as in the third option, use all 4 cores to run inference on a single model, and that is good if you want to optimize for latency rather than throughput. Now, if you take a look at the results in terms of sheer performance, you see that the 5 batch size single core option gives you better throughput than the others, and you won't know this ahead of time until you actually try different options, which is why I have this example where I sweep through different options, and you can sweep through these different options and decide which option works well for you. In terms of usage, what you have to do with AWS Inferentia is first go through a compilation step. There's a compile function that's available to you with the savemodel.compile, where you specify batch size and number of cores. And once you compile, let me show you the results of the compiler. The compiler will go through the steps, does graph optimizations, and finally gives you something called the neuron ratio. And the neuron ratio tells you how much of the model it's able to accelerate. If you have a very novel neural network with custom layers that are not accelerated on Inferentia, it'll partition the graph such that the unaccelerated parts runs on the CPU and the accelerated part will run on AWS Inferentia. In this case, with 99%, most of my model is running on the Inferentia chip. And running inference is pretty straightforward. You just load the optimized model and then you run inference and you get these final results I showed you. Now, with that introduction, let's take a look at benefits of using AWS Inferentia. So in terms of performance, Inferentia gives you some of the best performance out there, comparable to GPUs at much lower costs. It's an ideal option if your model is fully supported by AWS Inferentia. The SDK will tell you all the supported layers. So you want to take a look at that and then compare performance and decide. If you have very custom novel layers, a GPU is better because it's programmable and you can re-implement those layers in CUDA. In terms of cost savings, as I mentioned, Inferentia is one of the best option for cost savings, and some of the links we shared here on this slide are examples of lower cost, where you get lower cost with Inferentia compared to GPUs. In terms of ease of use, it's less easier to use compared to a GPU because deep learning frameworks come out of the box with GPU support. Here you have to go through a compilation step, but it's not that different compared to using NVIDIA TensorRT, where you have to still go through the compilation stage. And in terms of options, you have 2 options with single inference chips and 2 options with multiple Inferentia chips per instance. Again, the choice would depend on what kind of pre-processing, post-processing steps do you have. If you want to optimize for latency or throughput. If you want to optimize for latency, you want to get an instance type with more number of Inferentia chips, so you can spread out your model across multiple cores, so you can optimize it for latency rather than throughput. There are other things that you may take into consideration, such as whether you have custom layers or not. If you have a custom layer in your model, then it will fall back to CPU execution, so you want a more powerful CPU instance. Okay, so this was a summary of all the 4 different options. As we come towards the end of this presentation, we saw CPUs, which is a default option. We didn't discuss it separately because we saw comparison for it when using others. GPUs, then we saw elastic inference, which gives you variable size GPU acceleration. Then, of course, AWS Inferentia, which is a custom machine learning silicon. What I want to do now is take a step back and take a holistic view of all these 4 options. Let's spend a minute here to talk about where each of these options shine. So CPUs really shine with cost efficiency. They're not the most performant options out there, but with cost efficiency, it wins when it comes to smaller models. If you have larger models that demand more performance, then CPU may not be the right option for you. GPUs are really performant when it comes to some of the best performance for throughput and latency, and can be very cost effective if you can keep it fully utilized, like in offline batch processing, or if you're able to get continuous inference requests to keep the GPU utilized. And a big strength of it is that it's programmable, unlike some of the other options, just like CPUs. Elastic inference really shines with, again, just cost efficiency. It's not as performant as a full GPU because it's a variable size GPU, but it can be the lowest cost option if you have higher latency budgets, and you can meet those latency budgets using elastic inference, which is a lot more inexpensive. Finally, AWS Inferentia offers very high performance comparable to GPU, in some cases better. In terms of cost efficiency, it is a lower cost option than GPU. So if your model is fully supported, then AWS Inferentia can be the best option for you with Inf1 instances. Of course, it is not as programmable as a CPU or a GPU, but if your model is supported, then this can be the best option for you. So I'd like to wrap everything up with some resources. Here's a blog post that I've written that is a deeper dive version of this talk that includes a much more deeper treatment into all these different options. Be sure to check them out. The examples link below is the code examples that you would use if you want to replicate my benchmark results. I've also written topics on articles on other topics that may be interesting to you, all the way from distributed training to machine learning, experiment management, spot instances, debugging, and so on. The link is here. Feel free to check them out. And some resources for SageMaker examples that I showed today with sample code as well as documentation. With that, I'd like to thank you for taking time to listen to my talk. My contact information is here if you want to reach out to me if you have questions. Thanks again for listening.